Chapter 18, number 4. So this question refers back to problem 2, talking about character recognition, and successfully reads about 85% of handwritten credit card applications. So the population parameter for success is P equals 0.85. And in exercise 2, there were histograms showing simulations from sample sizes of 20, 50, 75, and 100. And then here are the statistics. So when the sample size was 20, the average number of characters recognized with the simulation was 0.8481. The standard deviation was 0.803, and so on. Now, if you notice, as the sample sizes increase, the mean stays the same. And notice that the mean hovers around or stays very close to, this is the experimental mean, if you will, the mean that they got with the simulations. It's very close to the theoretical mean of 0.85, what's considered to be the population mean. These proportions here are taken from the samples, and they're called p-hats. So the sample mean is 0.8481, 0.8507, and so on. And they're very close to the population parameter, which is symbolized by the letter P. The standard deviations go down, and the central limit theorem predicts that they will, well, it doesn't predict, but the formula for the standard deviation is the square root of PQ over N. And so the standard deviation should naturally decrease as N increases, since N is in the denominator. Then as N increases, the standard deviation will get smaller. And we'll see in a second, these are very close to the theoretical standard deviations as well, which is square root of PQ over N. So A, M equals 0.85, N equals 20, the standard deviation equals 0.0798. For N equals 50, standard deviation equals 0.05. N equals 75, the standard deviation equals 0.0413. N equals 100, standard deviation is 0.0357. So the simulations are approximately equal to the theoretical. They're very, very close. Now, which of these would be okay in using with the normal model? Well, either N equals 75 or N equals 100. Both their histograms are approximately normal. That is, they are bell-shaped and symmetric, and they both have NP and NQ is greater than or equal to 10. So if you do the math on that, for NP and NQ, when N equals 75, they'll both be equal to 10, so you can use the normal model. And the success-failure rates are listed in Part A. Let's see. Actually, I didn't list them in Part A. I must have done that earlier. Well, anyway, let me put those in very quickly here. So for N equals 75, NP equals 0.85 times 75, and that is approximately equal to, let's do this in the calculator here, 0.85 times 0.70 times 75. That's 63.75, which is greater than or equal to 10. And NQ is going to be 0.15 times 75, which is approximately equal to 11.25. Well, it's exactly equal to 11.25. Both of these are greater than 10, so the normal model is appropriate. Now, let's look at number 8. Okay. Class and by the M&Ms, you've probably seen the problem already, so they get bigger bags with 200 M&Ms each. Calculate the proportion of green candies they find. Now, if you recall, the probability of a green candy was 0.1. Why is it appropriate to use a normal model? Because 0.1 times 200 is 20. 20 is greater than or equal to 10. 0.9 times 200 is 180, which is greater than or equal to 10. So, assuming the bags are random and independent, certainly the M&Ms are randomly arranged in the bag, although we have an independence issue because the M&Ms are not infinite. We're sampling without replacing. Certainly 200 is less than 10% of the population of M&Ms, which probably is in the billions. And then we talked about NP and NQ. All right. So, and then they use the 68, 95, 99.7 rule to describe how the proportion may vary from bag to bag. And so let's look at the answer for 8 that I worked out. Let's see. Okay, here's 8. Okay, so n equals 200. Probability of a green is 0.1. The probability doesn't change, so we're going through the preconditions here. And A, 200 less than 10% of the population of M&Ms. Randomly selected bags, NP and NQ are listed here. Okay, now let's do the standard deviation is PQ over N. This is for a sampling distribution. So in other words, what is the sampling distribution? It's the distribution of the sampling proportion. So in other words, it's not the distribution of the entire population. The entire population distribution could vary or whatever. But you take a sample, and if you take a proportion from all of those samples, then those proportions themselves have a normal distribution, and the mean of that distribution is the population parameter, which in this case is 0.1. So the entire population of M&Ms has 10% greens. So the population parameter for greens is 0.1. Now, the standard deviation for the sampling distribution is going to be PQ over N. It's going to vary. The standard deviation is going to vary with every sample size, which makes sense. So for the green M&Ms in sample sizes of 200, it's the square root of 0.1 times 0.9 over 200, or 0.021. So we have a normal distribution for the sampling distribution of green M&Ms, the proportion of green M&Ms in samples of 200. So 0.1's in the middle, and then we have standard deviation 1, which is 0.1 plus 0.021, which is 0.121, and so on. So here is 1 standard deviation, 2 standard deviations, 3 standard deviations. Each standard deviation has 0.01, 0.021 added to it, and here's negative 1 standard deviations, negative 2 standard deviations, negative 3 standard deviations. And that's it. And so then you have the 68, 95, 99.7 distribution, C. As n increases, the standard deviation must decrease. Let's look at the formula again for the standard deviation. It's PQ over N. N is in the denominator. As n increases, the standard deviation must decrease. But the distribution will remain normal, and the mean will remain at 0.1. But since the standard deviation will shrink, the spread will shrink.